Hello, everybody. Welcome back. Navik, welcome. Hit the like button for good luck. Excellent. So say hi. Say hi if you're here. It's our last full week of class. Looks like there's just a few of us here today. Molly tuning in from Virginia. Good morning, Taylor. Hello, Helpy114. Have you seen the Humble Bundle book bundle, Applied Math Productivity? No, I have not. Emma, good morning. All right, we'll get started in about a minute or so. All right, well, it's 9 o'clock, so I'm glad you're all here. And that means you two in the, those of you who are watching this in the future, I'm also glad that you're watching this. It's time for our first simultaneous sip of a full week. So I think that's a good reason to celebrate. So if you have your coffee or your water or your tea, join me in the simultaneous sip. All right. So the plan for today and this week is we're going to just work on section 6.7. It's a little bit theoretical, but we'll go slow. We'll do a lot of examples. If you like this type of stuff, I recommend going on to take an abstract algebra class, because you do a lot of similar stuff in that class. 6.7. Inner product spaces. So in this section, we generalize the concept of the dot product. Okay, so let's start with a definition of what I mean by generalizing this concept of the dot product. And then we'll see a few examples. So an inner product on a vector space V is a function that to each pair of vectors u and v, in our vector space. Okay, so it's going to input two vectors in our vector space, and it's going to output a real number. Okay, so this is our notation for the inner product. Bracket, vector, comma, vector, end bracket. Okay, and so this is just going to represent some number. And it has to satisfy the following axioms. Okay, so this is the buildup. We're about to write the axioms. We have inner product. It's basically a function that inputs two vectors and it's going to output a real number, and it satisfies four properties. Okay, so the first property is it's commutative. We need the inner product of u and v to equal the inner product of v and u. Next, we want to be able to distribute it through a sum. Next, if you have a scalar times one of the vectors, you could pull out the scalar. And then last, which will probably be the hardest one to check, but we'll get good at it with practice, is if you take the inner product with yourself, it's greater than or equal to 0, and it's equal to 0 if and only if u is the 0 vector. A vector space that's equipped with an inner product is called an inner product space. Okay, so I know this may seem a little theoretical right now, but let's just check. Is it true that the dot product, is it true that the dot product is an inner product? So the vector space Rn with the dot product, and we'll show how to check this. Right, why is this true? Well, we could just show that the dot product satisfies all four of these properties. Right, u dot v is equal to v dot u. U plus v dot w is equal to u dot w plus v dot w. Cu dot v is equal to c times u dot v, right? We had a theorem that said all this. So these are the four conditions that have to be satisfied. And then last, u dot u is greater than or equal to 0, and u dot u equals 0 if and only if u is a 0 vector. Right, so to show something is an inner product, we're just going to go through and show that all four of these properties are satisfied. It's kind of the same method as like showing something was a subspace, right? We had to show that the 0 vector was in it, it's closed under addition and closed under scalar multiplication. We're going to do the same sort of checking, but we have four different properties we have to check now. Okay, so let's take a look at an actual example. And we'll see some applications of why this concept of an inner product is better than just having a dot product. Okay. So we'll let u and v be in R2. And again, feel free to ask any questions you may have. Okay, so we'll let u and v be in R2, and we'll let the inner product of u and v be 4u1 times v1 plus 5u2 times v2. Show that this is an inner product. All right, so does somebody in the chat want to explain how we're going to show that this is an inner product? And I'll give you a few minutes to try to work it out on your own. All right, so how are we going to show that this product here, 4u1 v1 plus 5u2 v2, is an inner product? Yeah, exactly. What Taylor said. Just go through and confirm that each of the four of these are true. So you want to do what UV is and compare it to what VU is. They should be the same. Similarly with 2, 3, and 4 might be a little tricky. All right, so I'll go through and work this out. Once we get to 4, though, I'm going to ask for some input. The first 3 are really straightforward. It's just a matter of checking. So UV is equal to 4U1V1 plus 5U2V2. Well, we can switch the order of U2 and of the U's and the V's, right? Because this is just multiplication of numbers. And this is V dot U, or V times U. Okay, so condition 1 holds. Now we do the same thing with condition 2, axiom 2. So that's 4 U1 plus V1 times W1 plus 5 U2 plus V2 times W2. Which we could write out to be this. This sum, 4U1 W1 plus 5U2 W2, that's the inner product of U and W. And this sum here, 4V1 W1 plus 5V2 W2, that's the inner product of V and W. So we showed that axiom 2 holds. Three, so we look at Cu times V. That's 4 Cu1 V1 plus 5 Cu2 V2. We could factor out a C. So condition 3 holds, and now we just want to show condition 4 holds. So we take the inner product of U with itself. which is 4u1 squared plus 5u2 squared. And so my question is, why do we know that this is greater than or equal to 0? Right, we want to show that this is greater than or equal to 0. Why do we know that 4u1 squared plus 5u2 squared is greater than or equal to 0? Yeah, because a squared number is always non-negative, right? It could be 0, right? So since, yeah, we'll call it, let's say x squared is greater than or equal to 0 for all x, like real number x, 4u1 squared plus 5u2 squared is greater than or equal to 0. And since x squared equals 0 if and only if x equals 0, 4u1 squared plus 5u2 squared equals 0 if and only if u1 equals 0 and u2 equals 0. Okay? So this is just another example of an inner product. There may be some applications where it makes more sense, instead of taking the traditional dot product, you do this kind of weighted dot product, where you care a little bit less about the first terms and a little bit more about the second terms, right? Because the reason why I say less and more is 4 is smaller than 5. But yeah, you could imagine there's going to be some applications where you want weights to these products. And so this is an example of an inner product. The dot product would be both of these coefficients are 1. But we could, change the coefficients here. 4 and 5 doesn't make any difference. And there's really nothing special about our choice of 4 and our choice of 5. Really, we just need them to be non-negative numbers. Right? If we had a negative here, then condition 4 wouldn't hold. All right, so let's look at another example. All right, here our vector space was R2, so we were dealing with vectors. But the whole point, like one of the main points of studying inner products instead of just the dot product, is it could give us we could kind of generalize the idea of the dot product to different vector spaces. Like for instance, the polynomial vector space. So let's look at that. Okay. So we'll let t0 through tn just be fixed real numbers. And they're distinct. Okay, so no two of them are the same and they're fixed. They're not variables here. Okay, so I could have given you the numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 if I wanted to, but we'll do it a little bit more theoretical. Okay, so we'll take two polynomials in Pn. Okay, so these are polynomials of degree at most n. And we'll define their inner product, or we'll define this product PQ by, we take P evaluated at T0 times Q evaluated at T0. And we do this for all products up to P of Tn times Q of Tn. Okay, so we would evaluate the polynomial at our first number, evaluate the other polynomial at the first number, and multiply them together. Plus, when we evaluate the polynomial at the second number, and do that product again, I'll add them up all the way until we hit every single number. Okay, and so what I want you to do is show that this is an inner product. Okay, and like the last example, the first three, conditions 1, 2, and 3 should be pretty straightforward to check. Condition 4 is actually a little bit tricky in this one. So once we get to condition 4, we could talk about that. So if you have any questions, again, please ask them. All right, I'm going to start going through showing this is the inner product. But obviously, you have the ability to mute me if you want to work on your own until we get to the hard part. So again, to show it's an inner product, we just got to show that all four of the axioms hold. Okay, so the inner product of P and Q, or sorry, the product, we want to show it's an inner product of P and Q, is this. And notice these are just real numbers here, so we can switch the order. Right, and so this is exactly the product of Q and P. Might need a little bit more space for condition 2, so I'll use the whole board down here. All right, well, maybe not. 2, we want to show that if we take the inner product P plus Q with R. Pick whatever letter you like. Well, this is equal to P of T0 plus Q of T0 times R of T0 . Right, and now we can factor this R of T0 in. Similarly, we can factor the R of Tn in. And then group together the PR terms, and then group together the QR terms. And we get that, yes, we can distribute the R through the plus, so that's great. Condition 3. That's a scalar, right? So we want to show that Cp times Q, which is equal to Cp of T0, Q of T0, well, we can factor out the C. And we're left with C times PQ. And now here's the one where I'm going to ask for a little feedback. Okay, so it's okay if your answer is I'm not sure, but I would like an answer from somebody. When we get the inner product of P with itself, we want to show, so we'll do this one kind of longer. So we want to show that P is greater than or equal to 0, and P equals 0 if and only if what? So we want to show that the product of P with itself is greater than or equal to 0. That's going to be pretty straightforward. It's going to be just like the last example. But we also want to show, I mean, like the last example, but our reasoning is going to be a little different, that the inner product of P with itself equals 0 if and only if something. What is this something? Fill in the blank. Right, if and only if P equals 0. But the question is, what does P equals 0 mean here? What is the 0 vector in this polynomial space? And I'll just answer it because there's a little bit of a delay. But we want to show that P is the function P of T equals 0. A lot of you made this mistake on the test when you were trying to show that, I don't know, the even functions were a subspace. You You forgot what the 0 vector was. It's not when you plug in 0 for t, it's the whole function is constantly equal to 0. Okay? So we want to show that this holds, and then we'll have to show this second part holds, which might take a little bit of thinking. Okay, so let's just look at what the inner product of p with itself, or the product of p with itself is. That's p of t0 squared plus p of tn squared. Since each of these numbers is non-negative, the whole sum is non-negative, right? Okay, so now my question is, why is it true? So why is it true that if this holds, then we must have the 0 polynomial? Why is that true? So if p, I guess the question is, if p evaluated at all n plus 1 of these numbers gives us 0, then it must be the 0 polynomial. Why is that true? I guess what I'm saying is, so let's ignore this. Another way to ask the question is, right, we want each of these values to be 0. Why is it true why is it true that if, right, this is basically what we want to explain this to show this part, right? Because we could just craft up an example to show that this might not work. There's something special that's going on here. Let's just kind of sidebar this. If p of t was the polynomial t squared minus 1, and t0 equals -1 and t sub 1 equals 1, right, then p dotted with itself would be, well, when you plug in -1, you get 0. So you get 0 squared plus 0 squared equals 0. Okay, so it appears to not work here. So what's going on here? Anybody have any ideas? If you don't, that's fine, but I would like a little feedback. Right, and this definitely is not the 0 polynomial. So there's something special happening in our case. Again, it's fine if you just put a question mark or a confused face emoji. It has to work for all n. Yeah, so that's the idea here. We don't have enough, right? We would need a third point. right? Because n is the degree of the polynomial, so we need t0, t1, and a t2, and then it would fail. The idea here, the big idea is, so I'm going to erase this. It's not terribly important. P is a polynomial of degree at most n. Which means P has at most n roots unless it's the zero polynomial. Right? And so for P inner product with itself to be equal to 0, we would need it to have not n roots, but n plus 1 roots, right? T0 all the way up through Tn. Right? The only polynomial of degree n that has n plus 1 roots is the polynomial that's constantly 0. All right, let's take a look at an example with actual numbers and actual functions. All right, so we'll let t0 equal 0, t1 equal 1/2, t2 equal 1. We'll let p of t be the polynomial 12t squared, q of t be 2t minus 1. Compute PQ and QQ. Using the inner product, using this inner product. All right, so let's start with PQ. So that's P of 0 times Q of 0 plus P of 1, P of 1/2 times Q of 1/2 plus P of 1, Q of 1. All right, now we can just evaluate these. P of 0 is 0. Q of 0 is -1. P of 1/2 is 3. Q of 1/2 is 0. P of 1 is 12. And Q of 1 is 1. So the inner product of P and Q is 0 plus 0 plus 12, which is 12. Similarly, Q dotted with itself, the inner product of Q and Q is Q of 0 squared plus Q of 1/2 squared plus Q of 1 squared, which is 1 plus 0 plus 1, which is 2. Okay, so we don't know what these numbers represent at this point. But yeah, this is how you would evaluate an inner product. Are there any questions on how we did this calculation? All right, if there's no questions, we could state one last definition. So we'll let V be an inner product space. So we'll let V be an inner product space with the inner product UV, some general inner product. The length of a vector the length or norm of V is the scalar. The norm of V is equal to the square root of V inner product with itself. Okay, so this gives us an idea of how to assign a length to objects like polynomials. Right, so for example, if we look at the previous example, if we look at this previous example, the length of Q is, well, it's the square root of when you take the inner product with itself. So it'd be the square root of 2. All right, so maybe it's not too terribly interesting to ask what the length of a polynomial is, but if we took the difference of two polynomials, we could ask how close is one polynomial to another polynomial using this idea of length or norm. Okay, that's what we'll think about tomorrow. This seems like a good place to stop. So let me know if you have any questions. I'll stay around for a few minutes. But if not, you have a homework due tomorrow night. I think it's pretty straightforward. So I'd get started. Just do it today and hand it in. Remember, smash the like button before you get out of here. It's so important. And the faculty have a meeting today about the final exam. So hopefully tomorrow I'll have some information about how we're going to do the final exam. Sorry, it's kind of been hidden, but we're kind of in a weird situation right now. Okay, so thanks for coming. I will see you tomorrow. Yeah, Navik, I'll check out that book. Humble Bundle book. Bundle Applied Math Productivity. Okay. Bye-bye.